introduce Dan. I think he's known in the community. So here's your mic. OK, go on.
Maybe we'll swap microphones. Am I on now? I think I am. I can hear myself. All right. Just to remind everybody what the problem is, Alice and Bob are suspected terrorists. Now, we don't even know that their actual names are Alice and Bob. We know we have to get their communications because they're suspected terrorists. All we know about them is that they're using WhatsApp, or maybe some Apple iMessage or something, or maybe TLS. They're somehow communicating, and we have to break their crypto. Now, the focus of this talk, of all the different ways that you could try to break what they're doing, you could say, look at what WhatsApp is doing, look at what TLS is doing, and try to find a weakness in that. But it's actually much more effective to go back in time and look at how the mechanisms that these protocols were selected, how these cryptographic mechanisms were developed, look at weaknesses in that. And this is not actually something that requires time travel. It's just something that requires thinking ahead. So what do we do to manipulate the standardization process? I should give some sources here, 2 web pages that you might want to look at for more information. There's badass with bada55.cr.yp.to, and there's projectbullrun.org. These have quite a bit more information, and there's lots of co-authors here listed there. Some of them are even here in this room right now. And I should also mention lots of previous work, in particular, really inspirational previous work from NSA. All right, so rewinding a bit, as Phil also did this morning, let's look at the data encryption standard. There were a bunch of arguments between IBM and NSA about what the key size would be for DES. And eventually, after the arguments converged, they settled on 56 bits for their keys. Now, that was all done privately. But then what happened when we announced this proposed standard publicly is, well, there was some backlash. So in particular, Diffie and Hellman were quite vocal in saying that the key size for the data encryption standard is too small. And this prompted NSA. We sent several people, actually, out to the West Coast to discuss things with the Stanford crew. So there were 2 NSA people, for example. There was Dennis Bernstein, who officially was working for the National Bureau of Standards. He was actually on our payroll, but sometimes you have to place people physically at locations where they can do some good. So he was at NBS, well, NIST nowadays. And so then there was this interesting discussion. There's actually a transcript online of a 1976 tape-recorded conversation between, with some funny stuff at the beginning. Is it OK if we record this? Ha, ha, ha. And then, anyway, this transcript ended up online with discussions between Diffie and Hellman and the NSA people and Bronstad, the NBS person. And I have an amazing quote here. I have to caution you, there was some nasty language. So if you're easily offended, then please cover your ears. But Diffie and Hellman were saying, your key is too small. And here's what Dennis Bronstad said. Fuck you, Diffie. My key is exactly the right size. The users love it. And you know, your public key cryptography is way too slow. Even your beard is too big. And then the conversation kind of degenerated from there. So there wasn't a lot of love already in the 1970s between the public cryptographic community and our friends at NSA and NIST. Despite the public objections, of course, we went ahead and standardized DES and kept promoting it for 20 years. The only public embarrassment that was serious enough for us to actually say, OK, we have to start thinking about maybe withdrawing this, was when EFF built a machine, the DES cracker, which actually was cracking DES keys basically instantaneously for only $250,000. And that was sufficiently embarrassing that, OK, eventually we had to withdraw DES. But in the meantime, having people use DES for, well, there's still people who are having their systems broken today in 2016 because of DES being used. And this is something where by starting a standard in the 1970s, which clearly had a key that was way too small, we had massive costs and security problems extending for 40 years after that. OK, another example of an interesting standardization process was DSA, and then subsequently ECDSA. After this was proposed by NIST, before NIST admitted that we had done it at NSA, Rivest was complaining about this publicly, saying, for example, that there was this random nonce, and this was giving the user enough rope with which to hang himself, something a standard should not do. So we go ahead and standardize that, and sure enough, various people like Sony get themselves hung by exactly this problem in the DSA standard. Which, okay, that actually caused enough public embarrassment that we had to do something. So we said, okay, let's add an option to the standard to do something deterministic, which will avoid this problem, while preserving all of the other options. So that's how you deal with a standard that's really going to encourage people to shoot themselves in the foot, is have more options so that maybe they'll choose the correct one, maybe they won't, and there'll be even more complexity for people to look at. The general pattern of what happens in these standardization processes, well, you'll see the same things today of key sizes too small, block sizes too small. We're still pushing things like that. We're still pushing error-prone standards. But we've actually adopted a new technique, which has been building up, which is flooding people with more and more standards to review. The main enemies that we have, the main people who are assisting the suspected terrorists, Alice and Bob, are these cryptanalysts or security reviewers or penetration testers or whatever. Let's just call them auditors. These people who are on behalf of the suspected terrorists looking for security problems in the cryptographic systems. And then sometimes they'll publish papers saying, this is broken, don't use it. Now, sometimes these people get together and they have a process like the SHA-3 competition that was mentioned before. There were 200 people around the world involved in this. Lots and lots of effort for years of really bashing on these hash proposals. And by the end of it, how could we possibly have slipped a security hole past all of this scrutiny? Let me tell you how. Here were the NIST standards published during the same period. Signatures, authentication, disk encryption, key wrapping, et cetera, et cetera, et cetera, et cetera. Now, while 200 people were busy looking at SHA-3, there were all these other standards being issued which had basically no review, except, of course, internally by us at the US government. I don't mean to exaggerate what happened. You can find examples of how not everybody was looking at SHA-3. For instance, there's an EAX prime proposal that I think was standardized by ANSI and was almost standardized by NIST, and then somebody in public said, you know, you can break it as follows, one-line attack. Okay, kind of embarrassing, but it was caught before NIST standardized it. The thing is that even if you might say, oh, this means that, yeah, of course, any weaknesses would be caught, there's lots more examples which show you that, no, weaknesses do not get caught. Even when they do get caught, they don't get caught quickly. For example, GCM had a serious mistake in the security proofs. Doesn't mean it's breakable, but it's something where the alleged reason for GCM being secure turned out to be bogus. And that was not published until something like 8 years after GCM's proofs were published, something like 6 years after GCM was standardized. The reason that this took several years was not that, oh, there was some scientific advance in cryptanalysis that had to happen. It was not that, oh, it was really complicated to find this flaw in the GCM security proofs. The problem was simply that nobody was looking at the proofs. And this was because we were carrying out this successful denial of service. We were publishing so many cryptographic standards that nobody could possibly review them all. And then, hey, there's weaknesses in some of them. We'll encourage people to use those. And then you were hearing before about how many different standards there are from ISO, for example. The public community, these auditors, these terrorist sympathizers, they are not going to be able to review all the different standards. There's another way that we can promote having more and more standards out there, which is just to lie to people about the need for standards. For instance, if you want to do a pseudo-random number generator, then of course you should reuse your ciphers, hash functions that you're using for other purposes. You can't do any better performance security than you can get by reusing your existing primitives. But we don't have to be telling Allison about that. We can just say, hey, you know, here's some better PRNGs. We'll just make up some reason that you should use some different PRNGs. And there's some more standards that you have to review. So, for instance, in 2004, we said, here's some number-theoretic random number generators which give you increased assurance. What is the actual argument for the increased assurance? It's bullshit, but that's okay. We can get people to spend time looking at these standards. We can actually standardize. So 2006, we had this standard for dual EC, saying that's the only DRBG, only deterministic random bit generator in this standard, whose security is related to a hard problem in number theory. Why is the problem hard? Why is it related? Doesn't stand up to examination, but that's okay. We can say it anyway. We're not getting punished for any of this. Another way you can stop people from having time to review all of your different standards is you can just ignore the attacks. So if a cryptanalyst says, hey, what you're putting out there, that's not secure, then you can say, well, you know, what you're doing, that's not really an attack, right? So for instance, 2006, immediately after this dual EC was actually published in a way that cheapskates like Andy in the back row, who was complaining about ISO being expensive. Okay, finally NIST puts out this dual EC stuff and the cheapskates get to look at it, and some of those cheapskates get to say, oh, this actually is clearly broken. Here's the attack. And of course, they were right. It fails the standard definition of what it means for a random number generator to be secure. So we go ahead and standardize, because we can just say, hey, you know, you've only broken some theoretical definition of security, but we can write down applications which are not broken. These biases that you're talking about, they don't affect my application, so we'll standardize. In other words, the auditors, they have to jump higher. They have to not just break the definition of security. They have to demonstrate an attack that breaks all applications. Well, okay, then there was this slight embarrassment of Schumau and Ferguson saying, hey, here's an attack which breaks, well, a whole lot of applications. Anything that exposes your RNG output, there is a backdoor in dual EC, which has a key that you might have thrown away or might not have in the first place, but somebody who does have the key can easily predict the future RNG outputs. And then Schneier had this essay in Wired saying, do not use dual EC under any circumstances. NIST and NSA have some explaining to do. So how do we respond to this? Well, we say, jump higher. Show us the key. You can't actually carry out this attack. We don't have the key. Of course, nobody has the key. We can't prove that nobody has the key, and we haven't done the minimal effort that would assure people that nobody has the key, but you can't show us the key. You can't actually carry out an attack. So, okay, we'll just claim that nobody has this key to the back door in dual EC and continue pushing this standard. We continue paying people to use the standard, which started in 2003. We'll continue issuing certificates, 73 validation certificates from NIST for implementations of dual EC. After there was this story in the New York Times about how, yeah, okay, we did have a key to this back door, at that point it became pretty clear that the standard was going to go away, that NIST was going to get rid of it, ANSI was going to get rid of it, ISO was going to get rid of it. But you know, that shouldn't stop the denial of service. So what we do at that point is we tell these researchers, you know, you still haven't done your job. Because even though, yeah, you say this is a really bad problem if the RNG output is exposed, is that RNG output really exposed in, say, TLS? And so there's this talk on video, Dickie George from NSA in 2014, June 2014, was saying, oh yeah, you know, these academics, they don't understand how hard it is to break this stuff. We can't possibly break, even if you had the key, which we don't, of course. Even if you had the key, we cannot possibly break dual EC used in TLS. And if anybody can demonstrate otherwise, I'll buy you dinner. Now, this is a master stroke, because you give free food to academics, and they're like, oh, yep. And so suddenly there's 10 people writing a Usenix paper. They're spending months on writing this Usenix security paper going, yes, you can break dual EC and TLS, and then where's that Dickie George? And he never pays up. I mean, you just offer people free food. It's amazing how easy these people are to manipulate. Okay, maybe the most important point that I want to make in this talk is the attack target that we have. So it's really important to understand that what people are traditionally targeting in cryptanalysis, in security review, is not actually the attack target. What people look at for, say, a random number generator is they look at a random number generator, like, say, dual EC or something else, and they ask, can I break it? Can I come up with an attack against it in whatever security model? Now, the assumption that the auditor is making here is that Alice and Bob are using the RNG, and their goal is to figure out if they can find any attacks on it. Sounds reasonable, But it's not the right question. Because the reality is that what's giving random numbers to Alice and Bob is not simply this last step of the process. It's not simply start cranking the RNG. What's actually giving random numbers to Alice and Bob is you start with somebody designs a system, somebody else designs another system, somebody else designs another system, we design a bunch of systems. They get proposed, they get evaluated by some complicated process, they get standardized by some complicated process, they get selected, and we can manipulate all of these things before things get deployed, implemented and deployed. We can change what the selection is, we can change what the standardization is. And that's the most important lesson of what happened with dual EC. Again, this is the most important thing that I'm telling you in this talk. This is not the same perspective, saying, here's an RNG, is this RNG secure? That is not the same as saying, here's the whole ecosystem that gives random numbers to Alice and Bob. Is that ecosystem secure? Example of the difference, if you look at ISO, and you look at their standardization process, and you say, okay, we would like to take over their standardization process so we can push out some random number generators, including some weak ones. We advertise this internally as an exercise in finesse, but if you understand how the ISO process works, this is not finesse. This is so easy. The economic costs of taking over the ISO process are minimal for any organization with a reasonable budget. It is trivial. There is no security to the ISO process itself. Maybe occasionally ISO standardizes something with some security, but we don't have to worry about that. As long as we get something weak into the system, then we can pay people, promote things. We can take these standards because that's all people want to see is, yeah, you've got a standard. Then they'll be easily influenced to choose the weak ones instead of choosing the strong ones. Another example of the differences between these concepts of what we're attacking. If you say, suppose that auditing is 90% reliable, catches 9 out of 10 of the weaknesses that you can come up with. Well, propose 20 standards that are weak, that you know are weak. And then maybe 18, 17, 19 of them get caught, but you'll get something weak through. And then again, you can pay people to use that one or otherwise influence them to use that weak standard. If you think that your attack target is one fixed RNG, then you don't get this kind of attack. It's only by seeing the whole process, the whole system that's taking lots of RNGs and choosing which ones to standardize and then selecting them, that's what gives you this kind of attack. The greatest thing about this, when an auditor realizes that, oh yeah, there is a bigger attack target here, and they say, oh my God, this is horribly weak, that's not an interesting paper. You try to publish a paper saying, oh yeah, it's trivial to take over ISO, here's how much it costs, then somebody will write reviews of that saying, oh yeah, that's of course a trivial attack, yeah, obviously. There's no sophistication to this. All you did was read the ISO manual and you understand how to subvert the system. What's the novelty there? And so you can't even publish papers saying these trivial attacks. Another example of changing the system, to segue into the next talk, changing from the system to the ecosystem. You might think Diffie-Hellman looks something like this. There's some elliptic curve which is God-given. And question is that elliptic curve secure when it's deployed by Alice and Bob? Well, maybe it depends on the choice of curve for elliptic curve Diffie-Hellman. But the actual system looks more like this. There's one little change in the picture, which is right at the top, which is we get to standardize a choice of curve. Maybe there's some constraints. Maybe there's some people watching what we're doing. Maybe they'll reject some choices of curves. But the point is that the security analysis here, our attack target here, is not the same as the attack target here. Just like any other change in the data flow can change your security, we get a huge difference in security between these two pictures. I thought since there's whole nother talk coming up, which I think will be focusing on elliptic curve rigidity, I would just give a brief example of what you can do to manipulate elliptic curve standards. The target here is Brainpool, which says, oh, those NIST curves, yeah, anybody could choose seeds for the NIST curves to manipulate those choices of curves. So the Brainpool curves are generated in a pseudo-random manner using seeds that are generated in a systematic and comprehensive way. Good marketing, you want this kind of thing to be in your standard. So here's the procedure. This is something where 10 years after the standard, we carefully implemented the procedure in the standard. for generating, for example, this is for generating the 224-bit brain pool curve. And the output of it, there's some weird things that happen. There's some big overlap between the supposedly random bits. That's funny. And then, well, OK, then we looked at the standard itself to double check and said, what did they say about this overlap? And the answer was that they didn't have the same overlap. They didn't have the same curve. The brain pool curve is not generated by our implementation, which is correct, of the brain pool procedure. The standard brain pool procedure does not produce the allegedly verifiably random brain pool standard curve. Now, you can fix it. So here's something where you can see the difference, right? There's the fixed brain pool curve. There's all sorts of questions which you might think that somebody should have to answer, but when you're standardizing stuff, you don't have to bother answering these questions. Even if you know there's this kind of question coming up, you never have to answer it. So even in 2016, these questions aren't answered. Did Brainpool know that there was this mistake in the Brainpool standard, that they had one procedure and another procedure, and this procedure is the one they said was their deterministic systematic one, and that one was the one that generated the standard curves? If they say that one of these is systematic and transparent and the other one isn't, then, well, does that mean their curves were not systematic and transparent? Does that mean that their procedures were not systematic and transparent? Something is strange here. Of course, they would say that both, if they were actually forced to answer this question, they would say that both are systematic and transparent, which is meaning that as standardization people, we get to choose which curve between the two systematic procedures. And in fact, we carried out this exercise quite a bit further, and well, okay, I won't go through the details, but the bottom line is that we generated more than 1 million curves, each of which sounds just like the Brainpool one. In fact, each of which sounds simpler than the Brainpool one, sounds systematic, sounds transparent, and we picked one which has, in red there at the top, is a curve that has badass in the coefficients. If you're interested in more information about this, well, again, there's a whole next talk coming up, but also, again, look at projectbullrun.org and badass.cr.yp.to, and you can get lots more technical details about how to manipulate stuff. As a final comment, in most countries today, it is Mother's Day, so remember to call your mom and wish her happy, healthy time and safety from Alice and Bob. Thank you for your attention.
Well, thank you very much. Are there any questions? Yes.
So Dan, thank you. This is a useful tutorial for me at my job. I appreciate
Welcome.
that.
This is John Kelsey.
Yeah, I'm a NIST person.
He's one of the Simon and Spec designers, I think.
Yeah, apparently. I can tell how this week is going to go already, right? Okay, I just wanted to point out one thing one of your slides kind of mentioned that I think is an important point worth bringing out and talking about. And it came out a little bit in the previous talk about algorithm agility. And this notion of algorithm agility meaning we have more algorithms.
Yep.
And that's actually it's not a useful security definition of algorithm agility. First of all, when you have 50 options, and everybody knows this when you look at security protocols, right, or security standards, if you have 50 options, you're guaranteed that some of them are going to be bad, or that they'll interact badly with each other. The other side of that, though, is the useful thing about algorithm agility is being able to stop using something. It's not being able to start using 10 algorithms. It's being able to say, this is broken, I'm turning it off. And that's something that people seem to miss more often than they get. They think, oh, well, there's one mandatory algorithm in this standard, and then I'll add 5 more that are optional. That can only make things worse in some sense. It doesn't actually save you if the mandatory algorithm breaks. And yes, I know we do a lot of publications, although I'll point out, anytime we are delayed on doing a publication or we don't do it quickly, we also get other people yelling at us because we're not, hey, how come it's taking so long to get format preserving encryption out? We've been waiting for this for 3 years.
Yeah, I mean, from my perspective as the attacker, I would say it doesn't matter whether you standardize too early or too late, as long as you standardize too much.
And if you don't standardize anything, if you don't write standards for any of these things, what happens then?
It's better to write many standards for each thing, yeah. And then there's tons and tons of ways that you're going to get something wrong.
So things that aren't standardized, people do a better job, do you think? I mean, like the key derivation functions in the literature that are widely used before there have been any standards for those, has that been better security, do you think?
See, it's great as the attacker. I just get to laugh at this whole situation and say, yep, you're screwed.
Thanks.
Other question?
Thank you. Thank you, Dan. This is very entertaining talk, and I enjoyed it. My question is follow with your previous question about the too many or too little the algorithms in it. And yeah, because we have different type of users from different regions, different countries for different purposes, and they require different algorithms they want to choose, they want to use, they want to make it for their life. Like the curves, some curves may be dodgy. I heard comments, I'm not going to tell you, say don't use anyone's curves, use Dan's curve. But we can't because, yeah, I'm sure you believe, I believe your curve's good, but not everybody will make the same choice because they do have their own view, they have their limitation, their purpose. Probably they also have pressure about what they can choose.
Yeah, so
all right, I would like to hear your comments. I'm not even ask questions, just some view.
yeah, so if you're trying to promote having as many standards as possible, then it's very useful to draw very fine distinctions between different use cases. So of course, PRNGs are a different word from ciphers. You couldn't possibly have the same standard doing both of those. And similarly, if somebody thinks that, well, they just like number theory better, then they should have some number theoretic hash functions, right? And there should be some number theoretic RNGs. Or maybe, there's people with different performance requirements. Clearly, it's very important to have a cipher with a 48-bit block size because hotel cards, whatever. I mean, you can just make up these things all day. It just has to sound good enough to get some people excited and enthusiastic because, researchers like this because they can publish more papers. Standardization agencies like this because they can publish more standards, which fundamentally is what they get paid for. And so this promotes more and more standards. Performance is fantastic because if you really look closely at performance, then you can draw all these fine distinctions. Of course, most users don't actually notice cryptographic performance, but if you highlight the cases where they do and say, ooh, this person cares about the area, and this person cares about the energy consumption, and this person cares about the software performance on a Pentium 4, which is still running in their server room, and this person cares about performance on a Haswell, etc. Then you can get all sorts of different algorithms looking good, and then you can try to say, let's take every algorithm that has any possible use case. And so you end up with a list of about 100 possible secret key algorithms and 100 possible public key algorithms. And then the auditor is faced with this complete nightmare. It's wonderful.
All right. Thank you very much. I think we should move on.